supposed to look at one of the two different calorimeters that we typically use in chemistry. One of them is called the bomb calorimeter. I'm not quite sure why they call it the bomb calorimeter, but really what it does for us, it keeps the reaction in a constant volume situation or a constant volume scenario. So let me explain a little bit more. So here we have typically a calorimeter, and we probably want to insulate it against the environment, so we want to put a nice insulation around the calorimeter like so that it's nicely insulated. We may want to put a little thermometer in there so we can measure the temperature of the water inside the calorimeter. But typically what happens is we put some reactants inside an enclosure that prevents whatever happens here from expanding the gases. So there's a certain amount of air involved there. And so we create a reaction between the reactants, typically by introducing a spark to get the reaction going. And then after the reaction then creates heat, that heat can then emanate through the enclosure into the water environment around the enclosure, but insulated from the rest of the universe, so to speak, so that we can then see that all the heat generated in this reaction then goes into the calorimeter and into the water itself. Why is it so important that we make sure that the reaction is such that it cannot expand the volume of the gases that are heated by this reaction? Well, that goes back to the first law of thermodynamics. The first law of thermodynamics says that the change in the internal energy of the gas, and that would be the gas inside this portion of the calorimeter, is equal to the heat added to the gas, which would be the heat generated by the reaction of the reactants here, minus the work done by the gas. And that's the key here, is that we want to see the change in internal energy recorded by the increase in the heat of the calorimeter to be equal to the heat that was generated by the reaction, but we have this minus W here. This is the work done by the reaction. And if you remember that the work done by the reaction is equal to the pressure times the change in the volume of the gases, so whatever the pressure is in here, times the change in the volume would cause energy to be taken up by the expansion of the gases, which we cannot do. We cannot allow that to happen, because otherwise some of the heat would be used to do work, and not all of it would be transferred into the calorimeter, and we wouldn't know how much heat was created, because we wouldn't know how much work was done. So we want to get rid of this portion. We want to get rid of that portion, and the only way we can get rid of it is by having no change in volume of the gases. So we put it in an enclosure so that gases are not allowed to expand. And if gases are not allowed to expand, then they can't do work, and so no heat is then taken away from the reaction to do work. And therefore, all of the heat generated in the reaction will go into the calorimeter, and that's what we want. Now, secondly, is one to understand how the calorimeter absorbs the energy. Well, for one thing, this bomb calorimeter has a certain amount of water around this canister right here, which will absorb the energy coming from the canister. Okay. Then in itself, the calorimeter itself, the enclosure, the box and all that, then in itself also has a certain amount of heat capacity. So what we have to then realize is that the heat gained by the calorimeter is gained by the water or the solution around the canister and the canister itself. So we have to then say that heat gained by the calorimeter is going to be equal to the MC delta T of the water. Remember that water heat gained by substance is always equal to the mass times the specific heat times the change in the temperature. Of course, we're going to measure the change in the temperature. We're going to know how much water we have, and of course, you know that the heat capacity for water, or I should say the specific heat for water, is equal to 1 calorie per gram per centigrade degree. To that, we have to add the specific heat, or I should say the heat capacity of the calorimeter. So we use the big letter C for heat capacity calorimeter times the change in the temperature. This, of course, would be the same change, and I should, of course, use the same T right there. Now, again, what is the heat capacity? The heat capacity is equal to the mass times the specific heat of the calorimeter, but usually we just have a single number representing that. So this is called the heat capacity of the calorimeter. And we're talking about the portion of the calorimeter not including the water, the calorimeter. Sometimes they just lump it all together. They know how much water is in there, they know the specific heat of water, they know how big the calorimeter is, they know the specific heat of calorimeter. They just lump it all together and then say the heat capacity of the whole thing times the change in the temperature. If they do that, we only have to worry about this portion right here. So some problems, they'll give you the water and the calorimeter. Other problems, they just give you the calorimeter by itself, including the water, and just put it all in one big number, saying the calorimeter will increase in heat, will increase in temperature by 2,000 joules per degree centigrade or something like that. And so we use the single number. Anyway, just be ready that you may want to add two of those together. And that, of course, is going to equal, remember, this is the heat gained. This will equal the heat lost by the reactants. And typically, this is, of course, the enthalpy, the heat released by the reaction. So the change in enthalpy. And, of course, if that's a negative quantity, then the reactants give off heat. If it's a positive quantity, then the reactants take in heat. And, of course, then heat will be drawn from the calorimeter into this portion of the calorimeter where the reaction takes place. Of course, then we're talking about an endothermic reaction. So that could happen as well. We may want to calculate how much heat the reaction absorbs as opposed to how much heat the reaction actually gives off. So that, of course, depends if the enthalpy is positive or negative. If it's endothermic, taking heat in, or exothermic, giving heat off. So then what you end up getting then is that the heat capacity of the water, MC, times the change in the temperature of the water, plus the heat capacity of the calorimeter times the delta T of the calorimeter. So the heat absorbed by the water plus the calorimeter part itself is equal to the delta H of the reaction. If the reaction gives off heat, the calorimeter of water will absorb it. If the reaction absorbs heat, the calorimeter in the water will then give off that heat. And we can then measure that by measuring the change in the temperature using the thermometer. And from that, we can determine the amount of heat either released or absorbed in the reaction. And that's what we call a bomb calorimeter. And remember, bomb calorimeter means constant volume, no energy given off to do the work. And so all of the heat generated or absorbed will cause the change in the internal energy of the calorimeter and the water. That's how you do that.